Gotta go live here. Hello, hello, testing. Good. Doing audio check. Make sure all this is working. And let's see if I can play this. Test. I think it's so. Looks like it's working. Okay, so sorry about that, guys. And here we are. Let me reorganize. Okay, what is the topic today? Now I have to go look at my video. What is the topic? Is the jet stream in collapse? Okay, so we're going to do some, I don't need this anymore. We're going to do some Earth system dynamics. Not my field of expertise. I'm a scientist. I'm a ecosystem biologist. The word system is in there. System scientists are not real common. It doesn't pay well, and it is really kind of a personality trait, or maybe a proclivity, that you want to know how, you want to see the big picture, you want to know how big things work. And there's not a lot of science in big things. There's science in little things, minutia, like where are the flowers and what type of flowers and where are they located on the map and stuff like that. Minutia. Tiny little subjects are called silos. So system scientists, like an ecosystem scientist, are rare. And it's almost like it's kind of a hobby, right? But I'm a system scientist. So when I started looking into Earth system dynamics 20 years ago, maybe longer, I became real interested in the topic and began applying my hobby to Earth system dynamics. The jet stream, the polar jet stream, let me change tabs here. Let's do this, okay? So this is Google. I did an AI search, changes in the flow dynamics of the North Polar Vortex. That's not the exact right way to word it, but it's often spoken of that way in the literature, so we'll stick with that. The polar jet stream, so there's two of everything. There's a northern hemisphere and there's a southern hemisphere. The northern hemisphere is north of the equator, and the southern hemisphere is south of the equator. The northern hemisphere contains the North Pole, and the southern hemisphere contains the South Pole. So we don't really talk about the southern hemisphere much. The South Pole is well inside of the Antarctic continent. The Antarctic continent is accessible. You can fly there. You can land on the ice. You can study the South Pole if you want to, but there's really nobody in the southern hemisphere. Significant exceptions are Australia, southern part of Africa, and the very southern tip of South America. Typically not large land masses and typically not a lot of people. And more significantly, sad to say, not the people who, can I say this, who count? Certainly not who count in science, because most of the science is done in the northern hemisphere. By who? By the Americans, the Europeans, the Japanese, the Russians, the Chinese, right? All northern hemisphere. So everything I'm about to say is about the northern hemisphere, and but it still mostly applies to the southern hemisphere. Therefore, since it is somewhat reflective, we can just start with one and not talk about the other. Long way of saying that everything I'm about to say applies to the northern hemisphere, but equally so in the south. So what is the topic? So the problem is that the polar jet stream there are two in the northern hemisphere. There's the polar jet stream and the subtropical jet stream. Again, not going to talk about the subtropical jet stream here, except to mention that it exists. But the polar jet stream is kind of a big deal. It determines, is this correct to say? It influences, let's say it influences weather. Weather is a manifestation of atmospheric physics. Atmospheric physics is a manifestation of Earth system dynamics. So Earth system dynamics, the winds, the oceans, the ocean currents, the high and low pressure centers, the atmospheric physics, all that stuff, the jet streams, polar vortex, the Rossby waves, all that stuff. All the various dipoles that occur, like the El Nino, Southern Oscillation, those kinds of things, all the dipoles. That's all Earth system dynamics. And what falls out of that is behaviors like the jet stream, which can be observed. Earth system dynamics is huge. This is the big engine. Earth system dynamics is studying the Earth as a dynamic system with its own various regimes of physics, atmospheric physics, oceanic physics primarily, but also even interactions with the sun. So solar weather, for example. And also the rotation of the Earth is part of the Earth dynamic system. So that's the big picture. And it's hard to focus on the big picture unless you're a systemic thinker, as you think of systems. So we generally go smaller and we talk about the subsystems. Atmospheric physics is really the topic today. So physics. On this picture you see here, well, I first did a Google search, changes in the flow dynamics of the North Polar Vortex. I could have left out the word north. It generally understands I'm talking about the north. So let's go through this. The long and the short of it is something is happening in planetary physics, in particular atmospheric physics. Something bad is happening. I'm not the first one to notice. A lot of people are mentioning this. I've kind of been noticing this for a long time. Other scientists have also noticed this and commented on it. Something bad is happening. But it takes a long time for an idea that may start with one or two people or a small team saying, excuse me, but something bad is happening. To have that idea spread out into the larger community, it just takes a long time. There's inertia in this system, and there's also firewalls. And any small group of people or a single person, just as often, can come up with an idea that's just bullshit. You know, the Earth is flat. Prove me wrong, right? So we do want firewalls. We don't want off-the-wall bullshit to propagate quickly out into the wider sphere, either on accident or on purpose, because it's bullshit. So why should we be talking about it? So there are firewalls, layers and layers of firewalls to review ideas, not to prevent them from propagating, but to review them. That's different. You see the difference? We're going to review this. Okay, it might take a year, it might take two, but we're going to review this, and we're going to talk about it among ourselves, and is it a good idea? If it's a good idea, then we propagate it outwards, and another group of people look at it. Then we propagate it outwards again, and another group of people, bigger group, takes a look at it. So about 10 years ago, oh God, maybe it's closer to 15 years ago now, I lose track of time, a very small group of people had a observation that something bad was happening in the north, involving the stability of the jet stream, the northern jet stream, and the stability of the North Polar Vortex. And that this was going to cause large-scale, eventually permanent changes in the Earth dynamic system, which would propagate into the entire planet, because the Earth dynamic system is the engine, and these smaller scale systems like the polar vortex are tied to that. But once the engine is changed in some way, then those changes propagate to all parts of the Earth, because the Earth dynamic system is global. The polar vortex may be only in the north, but the Earth dynamic system is global. So they were saying, look, man, we've got a problem here, and it's symptomatic of something bad happening with the Earth dynamic system. So they were looking at And you can see it here, the science behind the polar vortex. So they were looking at waves in the jet stream, and this picture, can I enlarge this? I really don't want to, but no, I knew that was a bad idea. Okay, so let's go back to this. Sometimes you don't get the images. Well, maybe I could. Is it down here? I don't think it makes. We're not going to get anything out of this. I'm sure it's an interesting paper, but we're not going to get anything out of that. So let's just stick with this picture on the right. The science behind the polar vortex. So the atmosphere actually occurs in layers, and most people know that, right? The top of the atmosphere is very near space where there is no atmosphere by definition. So the top of the atmosphere is what, 50, 60 miles up there, and then things like the jet stream, named because the jets have to fly through it. We first discovered the jet stream when we had high altitude jets, and that was like in the 50s after the war. So they named it the jet stream, and they discovered it and like, wow, what is this up here? And then the jet stream influences weather further down. So it's a stack, right? The polar vortex lives at the top of the stack, and it's positioned around the North Pole. The jet stream is a little bit bigger than the polar vortex itself, and it's positioned at about midway between the equator and the pole. The pole is 90 degrees north, the equator is 0 degrees north, and about 45 degrees north you get the jet stream. And the jet stream is not only lower down on the curve of the Earth, the jet stream is also lower in the atmosphere. We interact with it, and it interacts with our weather. So here's something about, and this is complicated, okay? This is Earth system dynamics. This is my thing, all right? This is my thing. I think in these terms easily. And there's a lot going on here. This isn't even my wheelhouse, right? But there's a lot going on here. It's really fascinating to me. I don't know nearly enough about it as I would like. And making things worse, we almost never hear anything about it, which is really too bad, because this is going to murder us. We're going to be murdered by this. It's already happening. Let me explain. So here's the basic science. The basic science is that there is a polar vortex, and they're showing it here. Let me get my drawing stick. I have a drawing stick. Here it is. Okay, good. So the polar vortex, if it isn't obvious, is this thing here, okay? And the polar vortex over here is this thing here. And they have it about the same size and shape, and that's not a bad start. The jet stream is a much larger, and they have it here as a circle, so I won't draw it again. See these arrows? The jet stream is created by the polar vortex. The polar vortex is a circular wind. I'll put an arrow on this. It doesn't always go in the same direction, by the way. It can reverse, and it can split, and it can do a bunch of other things. So, but it generally in the north, there's no one in the south, but in the north it rotates anti-clockwise, and it drives the jet stream anti-clockwise as well. The polar vortex is the driver, and the jet stream is the result. The polar vortex contains cold air. It's in the north. The air in the north doesn't get much sunlight, but it does radiate heat to space. So it loses heat easily, and it doesn't gain heat very easily. So it's cold. It's a very small area, though. The North Pole is small compared to, say, the equator. The equator is a much bigger area of the Earth than the pole. And so the fact that it's very cold up there, it is not as influential as maybe it might be, because it's a very tiny area. Also, the cold that is in the north is trapped in the north. And this is something most people don't understand. If you want to experience cold air, you actually have to go there. At least in the past. In the past, you had to go there. And of course, then you'd buy special gear. You'd buy special cold weather gear, warm things, parkas and whatnot. Your lined boots with the fur lined boots and all this kind of stuff. You'd have to gear up to go to visit the Arctic. I should be careful. If you wanted to experience, or let's say you're a scientist, you want to measure Arctic air, okay, then you would have to go to the Arctic. How would you do that? You'd get on a special airplane, and you'd fly, onto the ice up there somewhere, and you'd get out of your airplane, and you'd sample the Arctic air. You'd have to go to the Arctic to sample Arctic air, because the jet stream which circles at about 45 degrees, the jet stream acted like a fence. It's called a ring fence. The winds of the jet stream and their lower altitude reflection forms a wall of fast-moving air, a wall of air. And the air is moving so fast that it acts like a barrier to the movement of air. If there's a small gust of wind in the Arctic that's heading south, and maybe it'll gust all the way down to Canada, maybe the lower 48 states of the U.S., it can't do it because as it's gusting south, it hits the ring fence, and it just gets caught up into the fence and swirled around. So cold air masses from the north couldn't travel south. If you wanted to study Arctic air, for whatever reason, you're a scientist or you're a tourist or whatever, you want to experience that, you'd have to go there. But there's a phenomenon that's visible on the right side of this picture where the jet stream, which is the ring fence, it starts to break down. Now, this is where we get into another field of study that's called fluid dynamics. Fluid dynamics, fluids. What's a fluid? Water, oil, and air. Turns out the atmosphere, it acts like a fluid. It is a fluid. It's not a fluid you can float in. It's not a fluid you can pour from one container to another, but it's still a fluid and it has its own fluid dynamics. So what happens to the jet stream, which is a fluid, which has its own internal physics called fluid dynamics, is when it's moving very fast, the winds of the jet stream are strong, then it functions in what they call laminar flow. Laminar flow. It's just straight, like water coming out of the tap. You turn your tap on and a stream of water comes out, goes into the sink, but it's straight. It's laminar. When that same stream of water, or in this case jet stream, when it slows down, it begins to the laminar flow begins to break down, and instead the fluid dynamics at slower speeds cause it to meander and to create eddies, vortices, and you can see this easily if you want to. You can take the water coming out of the tap is going into air before it hits the sink, and the water coming out of the tap is heavy enough to resist the air and not be interfered with. It just goes into the sink. But if you pour water into water, like into like, then you get a completely different behavior. It's nonlinear. There's no laminar flow. They mix. If you take colored water and pour it into uncolored water, clear water, and you pour it in, it drops out of your first container in a laminar way, straight. But when it hits the clear water, it immediately slows down and starts to spin like this. And it's called mixing. And these fluid dynamics, they were very difficult to study. People understood that there was something going on, that when you pour water from a container through air, you get one type of behavior. And when it hits other water and starts to mix, you get a second type of behavior. And they knew that. And they said, wow, this is interesting. What's this about? And, it took the invention of high-speed computers before they could start to simulate these things and therefore study the equations of fluid dynamics. But what they discovered was when fluids, and again, the atmosphere is a fluid, when fluids are moving swiftly, they behave in a linear or laminar way. When they slow down, they behave in a wavy, chaotic way. And you get eddies and spins and vortices, and it's all very complex. It can't be simulated. But like a lot of things I've mentioned on this channel, it contains non-linearities that are chaotic in nature. So when you are pouring one color of water into a different color of water, the mixing is chaotic. It's predictable, by the way. That doesn't mean we can't predict it. It is predictable that it will behave that way. And this is something that people don't understand about chaos. Chaos is completely predictable. You can pour blue water into clear water, and it will mix. That's completely predictable. It won't simply go through and then collect at the bottom. It will mix. That is completely predictable. But the way in which it mixes is chaotic. See, two things can be true at the same time. So what happens with the atmosphere, and we're talking about the jet stream here, what happens with the jet stream is that when it's strong, the fluid dynamics are laminar. When it slows down, the fluid dynamics become chaotic and nonlinear. It even appears nonlinear. You can see it mixing, the vortices spin off and things like this. I'm just talking of the atmosphere as a fluid. And you can do the colored water thing yourself. You can pour it out of the container and it comes out straight until it hits the other container. And as soon as it hits that other container, it slows down. And when it does, it becomes chaotic. And the chaos is predictable. I can't say that enough. Yes, it behaves in a chaotic way, but the chaos is predictable. It will happen. It's guaranteed to happen. But how it progresses is random, chaotic. It is so predictable and it is so easily modeled that we can actually use computers to make really accurate and convincing renders of fluid dynamics, chaotic flow in fluid dynamics. For example, pouring colored water into transparent water. So this is happening to the jet stream now. The jet stream is evidencing fluid dynamics. It is a fluid, and the atmosphere is a fluid. Therefore, it has the properties of that come from fluid dynamics. We can study it. We know that if anything ever slows down the jet stream, then it will begin to meander and throw off swirls and mixes in a chaotic way. But that's predictable. It will do that. We don't know when it's going to do it. We don't know how it's going to do it. We don't know how it's going to progress. But we know that it will do that. It is predictable that it will become chaotic. This is hard to understand. That two things that sound like they're opposites can actually be true simultaneously. And according to physics and mathematics, they must be true in this case. This is physics. The physics of fluid dynamics, which only really became a mathematical field of study 50 years ago. I mean, we knew. Everyone knew. We've known for thousands of years that there was something there, but we couldn't really study it. Now we can. So here's what's happening to the jet stream. I'll stay with this picture a little bit longer. The right-hand side of this picture in the upper right shows what happens when the polar vortex becomes weakened. And I guess I'll clear this drawing. The polar vortex becomes weakened. They're calling it stable and wavy. There's something like that. This is confusing, and I don't think anybody really has sat down and defined their terms properly, because I make this mistake too. The polar vortex does not become wavy as such. It can split and become bipolar, which sounds bad, right? It can split, and it can move. It's supposed to be right around the North Pole, but it can move. It can slide off the North Pole and slide back, and it can also split and become two rotations. And this has been studied quite a bit. In fact, one of these pictures further down, maybe I'll just go ahead and click on this one. I think this one's probably the better of the two. Here it shows on the left a stable polar vortex, and then it shows on the right a disrupted polar vortex. So these are now the correct terms: stable versus disrupted, stable versus unstable. It doesn't really become wavy. The waviness is a manifestation in the jet stream. When the polar vortex is strong, then the jet stream is strong. When the polar vortex is disrupted or weakened, these are the words we need to use here now, then the jet stream slows down. That's the coupling. When the polar vortex is strong, the jet stream is laminar. When the polar vortex is disrupted or weakened, and the two kind of go together, they're kind of almost synonymous. Not quite, but they go together anyway. Then the jet stream becomes delaminated and becomes meander, becomes wavy and chaotic. And all those things go together. They're not quite synonymous, but they all go together. So going back to this picture. Oh, wait. This picture. So these systems, these are coupled systems. The polar vortex, its behavior is coupled to the jet stream. And the jet stream is what's critical to our weather. So I'll get to that in a moment. But I have to discuss Earth system dynamics. I just can't do this. I can't do this topic today without, which is discussing the jet stream and its imminent collapse. I can't discuss this without first introducing Earth system dynamics. Yes, this sucks. This is PhD level bullshit, okay? I don't even think they teach this in meteorology school. You can get an entire degree in meteorology. I don't think they ever mention any of this. I've certainly never heard a meteorologist mention any of this stuff. I think maybe last year or two, we start to hear meteorologists who talk about the weather, right? The weather tomorrow, the next 72 hours. They're starting to kind of talk about this a little bit. Maybe they're picking up their knowledge at conferences. Maybe they're talking among their peers. Maybe they're watching YouTube videos, right? Maybe they're watching this one. So I don't know. But the meteorologists seem to be catching on to it. And of course, again, the nested dolls, the hierarchy is your local weather is driven by atmospheric dynamics, like the jet stream, like all the dipoles, the ENSO being one of them. Your weather is driven by atmospheric dynamics. Your atmospheric dynamics are driven by Earth system dynamics. Okay, that's the nested dolls. Weather driven by atmospheric physics, driven by Earth system physics. So right now, when I'm talking about this, I'm talking about atmospheric physics. But there's a big system out there driving all of this. And I don't have a lot of visibility into that. I'm a system scientist, so I get it. I totally get it. But it's a field of study I have not spent a lot of time on. I don't intend to. I know it's there. I know it's important. And I'm telling you that it's important. And it's important to the topic today because we're fucked. Oh boy, we're in big trouble. We're in big trouble, people. Whoa. Whoa, whoa, whoa. We're in trouble now. So let me go over here and read from this AI overview. The AI overviews, at least for the science, are actually pretty good. I keep hearing people say, oh, AI overviews, AI summaries on Google, they're bullshit. And I'm like, this is pretty good, actually. I mean, I know the topic, so I can evaluate this as a AI overview of the topic. The topic was changes in the flow dynamics of the North Polar Vortex. You're not going to do that as a query. Why am I doing that as a query? Because I know it's a thing, okay? Because I'm a system scientist, right? That's the page we're on here, people. That's my wheelhouse. So I can query like that, and when I do, I get the right answer. So it's encouraging to me that I'm, on the right track. And this is the topic. Changes in the flow dynamics of the North Polar Vortex. This is the topic. You're all going to have to know this. I mean, you don't have to become an Earth system dynamicist. You don't have to be an atmospheric physicist. But you need to know this stuff. This is your life now. You're not ready for that. You don't even believe me when I tell you that. But yeah, you're all about this. And I'm going to be talking about this a lot. I'm going to tell my wife this morning, Jesus, I gotta stop worrying about my property and worrying about my breakfast. I have to start doing this. We're in big trouble, people. I don't know how to tell you this. We're in big fucking trouble. We're in such huge trouble. This is gonna hurt so bad. We are gonna hurt so bad because of this. And I just want you to know, this is bad. So let me look at this. Changes in the North Polar Vortex flow dynamics are typically characterized by weakening, wobbling, splitting, or shifting. So yeah, the North Polar Vortex can do all those things. Principle to today's topic is weakening and splitting, okay? Driven by strong atmospheric waves that can cause a sudden stratospheric warming. This is critical, and I want you to focus on the word warming. Warming. Where does that tie into the topics that I cover most often? Global warming, sudden stratospheric warming. Okay? You getting the picture? Sudden stratospheric warming causes strong atmospheric waves. This disruption in the stratosphere affects the jet stream, leading to wavy patterns that can bring cold Arctic air into the mid-latitudes. That's you. That's me. You don't know you're living in the mid-latitudes, but you do. Causing sharp temperature drops and influencing winter weather. Actually, now it's actually so bad now that it's influencing fall weather and spring weather as well. There's a lot of cold air in the north in the winter, and so long as the jet stream was strong, it could be a ring fence and keep that cold air in the north in the winter. But now that the jet stream is actually collapsing, and that's because the polar vortex is weakening. Now that the jet stream is collapsing, that cold air can spill out of the Arctic. And I have made a point of not calling that weather. Your weatherman will tell you, oh, we're going to have record cold. And you'll say, record cold. It's going to be cold weather. No, it isn't. Weather is a local phenomenon. And to focus on this as a local phenomenon is to completely miss the forest for the trees. This is Arctic air. It's not supposed to be in the mid-latitudes. Something is wrong. Something's wrong, people. It's not supposed to be there. Normally, if you wanted to experience Arctic air for whatever reason, you'd have to get in an airplane, fly to the North Pole, land on the ice, and walk outside the airplane, take a deep breath. Arctic air. But now you don't have to do that. It breaks off. It breaks off of the North Pole, and it slides south, and it affects North America, as far south as Florida. Record low temperatures just recently, a couple of weeks ago. Record low temperatures, way below freezing in Florida. And it also affects Europe, Asia, right? Well, Eurasia is one continent, but you know what I mean. So when this Arctic air slides south, and it can do it at 100 miles an hour. It comes really fast. High winds, frigid cold. It's so cold up there, people. No one goes to the Arctic. You have no idea how cold it is. But just wait long enough, and some of that air will come south and find you, because the jet stream is breaking down. And it's not weather. It's not weather. You're experiencing something that we call atmospheric physics, atmospheric dynamics, Earth system dynamics. This is something critical. It's falling apart in the Earth system. It's called the jet stream. It's driven by behaviors of the polar vortex, and the polar vortex is weakening. It's not as cold as it should be. And why is it not as cold as it should be? Because of sudden stratospheric warming, and overall because of global heating. So now we come full circle. You get enough global heating, you're going to get warming of the polar vortex, and that's going to become permanent. And as the polar vortex warms, then the jet stream slows down. That's going to become permanent. And as the jet stream slows down, it becomes weaker as a ring fence. Therefore, Arctic air can finally spill through it. That's going to become permanent. And the progression of this process, has the polar vortex warm enough on a permanent basis because of global heating, warm enough on a permanent basis that the jet stream is permanently degraded on a permanent basis. And therefore, Arctic air can spill out, head south, in particular in the fall, winter, and spring, on a permanent basis. This becomes normal, not abnormal, not a one-time 100-year event, but an every year event, up to 20, 30 times a year. Because the ring fence is gone. The jet stream is just gone. It can't do what it did. It can't be a fence. It can't hold anything back. And at the same time this is happening, now I'll mention this on this image on the right. You'll notice that not only does cold air move south, but warm air moves north. That has to happen. If you have an air mass moving from the top of the world towards mid-latitudes, cold air, breaking through the jet stream, then there must be, at the same time and to the same degree, a warm air mass from the mid-latitudes moving north to replace it. It's the yin-yang again. They're just trading places, because you can't have air leaving one place and have less air. That's a vacuum, relatively speaking. So it's going to pull air in from someplace else, and that someplace else has to be from the south. So when we are getting cold air, which we are now getting cold air here in the lower 48. I can't speak to Europe or the UK or Asia, but here in the lower 48, we have been getting these cold air masses slipping off of the North Pole about every week, maybe every week and a half or two. This is so frequent and so catastrophic that even meteorologists are beginning to notice. They don't talk about it in the terms I'm talking about it here, and you can understand why. This is complicated shit. No one wants to talk about this. This is not my weather 72 hours out. Do I need an umbrella or not? Do I need to wear my warm coat today because it's going to be freezing when I come home? What do I have to do? No one cares about this stuff. But this is the stuff that's going to destroy you. This is going to kill you. A massive breakdown of the Earth dynamic system is going to change everything. And why would it not? Why would it not? And specifically, with all this warm air breaking to the north, it's going to do what now? What does warm air do in the north? It melts the ice. And what does the melting ice do? Well, if it's land-based ice, then it flows into the sea. And what happens when melted land-based ice flows into the sea? Sea level rises right now. We have a lot of land-based ice on the island of Greenland and in Canada, and of course every part of the world above the Arctic Circle. So northern Russia, the Scandinavian states, Iceland, right, places like that. They will melt, and their melt water will flow into the sea, causing an increase in sea level, a slowdown, and eventually a shutdown of the AMOC, another topic. And these things then become irreversible. It's called catastrophic failure, terminal decline, catastrophic failure. A catastrophic failure of the AMOC is inevitable and irreversible. A catastrophic melt in Greenland is unavoidable and irreversible. They're losing the alpine glaciers in Switzerland, and the landslides are coming down and burying the villages that have been there for 900 years. And they're burying the villages, and people are having to abandon their communities. And why are the glaciers melting? Because it's just too hot. The planet's too hot for ice. Can't have ice on a hot planet. You just can't have ice. That's why we have to call this global heating, because global heating tells you what's going to happen. The ice is going to melt. Ta-da. And so that's why we have to use the right words, folks. It's global heating. So let's continue with this. Key changes and their impacts. So I'm reading this because, at least in part, I want you to understand that this is fucking complicated. It is. But this is it. This is the deal, people. This is the deal. You don't have complication in your life right now. Your life is pretty simple, right? You got your routine. You got the things you got to pick up every week at the supermarket. You have to fill up your car twice a week or once a week. You have a schedule for that. You know when you're going to do that. And you have to meet with your friends, and you have to get your kids to and from school, and you got your patterns, right? And while you're doing all that and you think you got a handle on things, this shit's happening. And it's complicated. And you think your life is complicated. Just try yourself some earth physics. Just try yourself some atmospheric physics. Oh boy. This is wild. This is a wild ride, okay? This is a wild ride. And I don't feel bad that the meteorologists don't want to go there. This is a wild ride, people. This is it, though. This is the real deal. This is your actual future we're talking about here. Yours, mine, everybody's. Because we live in the mid-latitudes. This is us. We're on deck here, okay? We're queued up for some some hard times, okay? Key changes and their impacts. I'm just going to read this. We're talking about changes in the North Polar Vortex caused by sudden stratospheric warming. That was a mystery a few years ago. The last time I heard anyone talk about sudden stratospheric warming SSW, they were like, "Yeah, we don't really know why that happens. I don't know." Well, okay, we've got global heating going on, so that's going to have to play a role somehow. But they're like, "Yeah, we just don't know. I don't know, Rossby waves, dipoles. It's hard to say what's happening here." All right, so I think they know a little more about it now than they did a few years ago, last time I heard somebody lecture on this. Key changes and their impacts. Weakening and splitting. A strong polar vortex is a stable circular flow that keeps Arctic air contained. When it weakens, it can stretch, wobble off center, or even split into two or more smaller vortices. Strong polar vortex. Let me throw another definition on top of strong. Strong is also true. Cold. Polar vortex. When the polar vortex gets warm, i.e. sudden stratospheric warming, then you get problems. Okay, so you can call it strong, but it's strong because it's cold. Okay, cause and effect. I can show you a polar vortex that is broken, because it's broken right now. And I'm going to earth.nullschool.com or .net. We'll find it out. And real-time data of atmospheric wind effects. This is a mid-altitude view of the North Pole. This little green dot in the center, I think you can probably see it. There's a little green circle in the center. That's right over the North Pole. And the U.S. is in the lower part of this sphere. So we're looking down on the North Pole, so you can still see the northern hemisphere, but the continental U.S. is way here at the bottom, and I can get my drawing stick. Yeah. So the U.S., the continental U.S. is sort of here, okay, and Alaska, the state of Alaska, is about here, and the U.K. is right here. There's the U.K. What else can I draw in here that people would use? It's also kind of hard to see what's going on with these wind flow diagrams, but in any case, I think you get it, right? So, and of course, this little thing here in the center, this is the North Pole. We are looking down on the North Pole. So this, the lines, you see purple lines, red lines, green lines, these are wind flow speeds, the power of the wind, and this is at 500 hectopascals, which is at about, I don't know, 15,000 feet or so a couple miles up. This would be the jet stream. It's probably like 5 miles up. This would be the jet stream. And the jet stream, again, is a wind pattern. It's supposed to be a circular ring fence that is a manifestation of the behavior of the polar vortex, which is higher up in the atmosphere. So this is the jet stream, and we'll talk about this in a moment. So I'm going to turn off my drawing, and now I'm going to go to a really high altitude. So this is really high up in the atmosphere, top of the atmosphere view. And this is the polar vortex. Now, and again, that green dot in the center, that's the North Pole. I did not change the view. I just changed the altitude. We're higher up in the atmosphere now. So, yeah, this is earth.nullschool.net. And it's got a pretty simple UI, but you have to know what you're looking at, right? This is a hardcore science, people. This is hardcore physics. This is atmospheric physics. And where are you in that topic? Well, figure it out, folks. This is the rest of your life. So this is the polar vortex viewed from space at the North Pole. Now you can see all these purple, pink, red lines that are going around in a circle anti-clockwise, which is what it should be. I mean, it's counterclockwise, right? That's the polar vortex, but there's two of them. There's one going anti-clockwise, that's the correct one. And there's another one going clockwise. It's smaller, the winds aren't as strong, but neither one of these is positioned over the North Pole. So this is a split polar vortex. This is bad. This is really bad. This is about as bad as it gets. The only thing that's worse than this is if it really slows down completely, or it becomes trimodal, or it just disappears. That's worse than what we're seeing here. But this bimodal behavior of two rotating vortices geared together, one of them clockwise and one of them anti-clockwise. This is what they're talking about, that the polar vortex high up in the atmosphere becomes weakened, wobbly, split, okay? And what it is it's warmer. It's warmer. When it warms, these behaviors manifest. Why is it warming? Because of something called, an observation called sudden stratospheric warming. And what causes that? Well, I don't know. If people have hemmed and hawed, they don't really know what's causing it. There may be better science about it now. But you know what? It doesn't matter. It's an observation. Sudden stratospheric warming leads to a weakening of the polar vortex, which means that the polar vortex can move, split, and do some other things. When it does that, then it has impacts on lower altitude. Same orientation, but lower in the altitude, like the jet stream. So we can go to here, which shows us the jet stream. Now, the jet stream is supposed to be a ring. It's supposed to be, okay, it's never a ring. Not usually. It's always got some fluid dynamics because it's a fluid. But it's supposed to be more of a ring than this. There are parts of this ring that actually extend way, way south. This is not even polar anymore. This thing is behaving in the lower mid latitudes, like down around California. We're getting, or really anywhere that's south of maybe 45 degrees north of latitude. There's lots of places now that are being affected by the jet stream, and it's falling apart. You see all these lobes. You see this thing breaking off down here around California. This has been really affecting our weather, this kind of thing here. We've had, I want to say like 4 or 5 of these loops that came down as far as California. That's the jet stream. It's not supposed to be there. And then when it gets that far south and it's meandering and it's falling apart, it actually generates cyclones. Cyclones. And if you live in Australia, you know what that is. Here in the northern hemisphere, we don't call them cyclones, we call them hurricanes and typhoons. So normal hurricanes, normal typhoons, and normal cyclones in the southern hemisphere are warm core circling air. Warm core. They form over warm water and they contain warm air. And the warm water drives their rotation, and you get hurricanes in the Gulf of Mexico, the South Atlantic, and you get typhoons in the South Pacific. Different names, same thing. I don't know why there's different names. And they're all generically cyclones. And the southern hemisphere, has the right of it. They call them cyclones, and that's what they are. A cyclone is a rotating wind. For that matter, even a tornado is a cyclone. These are rotating winds. But we call them hurricanes and typhoons, and don't ask me why. It's dumb. People are inconsistent. So we've been having cyclones coming down to California. We're not calling them typhoons. We're not calling them hurricanes, and they're not warm core. They're not forming over water because of interactions between the atmosphere and the ocean and the heat content of the ocean. But they are cyclones. And we're getting cyclones off of California. We've had a few, but they did not come from the south. And they're not warm core in the center. They come from the north, and they're cold core because they contain Arctic air. So what's spinning them up? We know what spins up a hurricane. It's the warm surface waters of the underlying ocean. It's underneath the air mass, and it causes it to spin. Well, the Coriolis effect causes it to spin. But it's the energy of the warm water that causes a warm core cyclone, like a hurricane, to spin. So what's causing these ones from the north to spin? Well, they're not over warm water, so that is not the dynamic. They are cold core cyclones, and we're getting a lot of them here in California, and it's been really extremely damaging. Even the meteorologists are noting that. And they're saying things like, this is not right. Why are we getting cyclones off the west coast of North America? Why are we getting cold core cyclones that are bringing, frankly, just to be honest, devastation to like Southern California? they are being beaten to pieces, one after the other of these things. We've been on the edge of them a couple of times, and here in the Bay Area, and the amount of rain is pretty epic. And we're not really, I mean, we're starting to get into the rainy season, but we started having these cold core cyclones coming down from the north like a month and a half ago. It was still summer, and all of a sudden these things started coming down and sliding in off the Arctic with a cold core. And what, the rain doesn't come from the cyclone in this case, because it's a cold core cyclone. The rain comes from interactions with hot, moist air in the south. And that's what's been destroying Southern California. They're getting rains from these cyclones that are almost impossible to comprehend. Wow, they got big problems. And their problems begin because this is not weather. I know you'll get your 72-hour forecast and they'll talk about the weather, but this is not weather. This is different. There's something going on here. And it's a collapse of the jet stream ring fence. And these cold core cyclones are breaking off of the jet stream. The jet stream is a circular wind. It goes in a circle. You can see it here in this diagram. It's going around. It's got bumps and waves and braids and a bunch of other things, but it's rotating. And when part of it breaks off, it's called a cutoff low. When part of it breaks off, it also circles. It borrows the angular momentum. It actually steals some of it. Every time we get one of these cutoff lows, it slows down the jet stream, which is also going in the wrong direction. You see? And just keep that thought in mind. Every time one of these cutoff lows breaks itself off of the jet stream, it steals angular momentum from the jet stream and slows it down. This is inevitable. This is physics. This is conservation of momentum. This is basic physics, folks. And if you're not up to speed on your physics, then this is going to be really confusing to you. It's going to seem like magic, and it's going to seem like gobbledygook, but it ain't. This is it. This is your reality now. And 20 years ago, you didn't have to worry about this stuff because it didn't have much effect on you. But now it's coming. This shit is on the way. It is here. This is the real deal, people. I don't know how to say this. You're going to have to toughen up. You're going to have to get yourself some physics. You're going to have to understand the Earth dynamic system. I've been working on this for 10 goddamn years, and it's complicated, and I'm starting to figure it out. But, man, you don't have 10 years to figure this out. This shit's coming for you now. It is coming, my dudes, my dudettes. This shit is coming, and Southern California is getting a taste of it. Cold core cyclones breaking off of the jet stream, bringing cold air and interacting with hot, moist tropical air and creating rainfall events that are gobsmacking, ruinous. And this never stops. It may be worse some times of the year than others, but it can't stop. There's no end to this, because this is not weather. This is not the normal cycle. This is not even the seasons. This is a breakdown of the Earth dynamic system. This is, I have to turn off my drawing tool. This thing, a bipolar, polar vortex, driven into this configuration by sudden stratospheric warming. And warming is in the name. And what else do we know is warming? Catastrophically, the entire planet. Global heating is driving this. Global heating is driving all of this. And this behavior in the polar vortex will become permanent. Permanent. Cannot be avoided. This is baked into the cake now. This is Earth system dynamics. This is atmospheric physics. The planet is warming. It is heating. The heat will make its way to the north and it will fuck things up. This becomes permanent. This becomes a feature of every single day. More or less, but every single day. This is permanent. And that drives this. And that's why California is getting all these cutoff lows that are fucking us up. That's why the southern U.S., and you're going to listen to Max Velocity, he'll talk about it all the time, because he talks about the Midwest and the South and the Southeast. They've been getting waves of air masses. They had, this was back to back, this was like 3 weeks ago, back to back. They had a massive Arctic air mass break off of the North Pole, descend south, and freeze them solid. All the way to Florida. All the way to Florida. Record low temperatures. Multiple record lows were set during that period of time. And then, 4 days later, record heat. Record heat because, again, over here, sometimes you're in a lobe. Give me a drawing tool back. Okay. Sometimes you're in a low that's bringing down cold Arctic air. And sometimes you're in a lobe that's bringing up record warm air from the equator. And these lobes follow each other around the planet. They move from west to east, and you're stationary, but they are not. And as they progress from west to east around the rim of the planet, they just go around and around. They bring cold air on one day, and then the next day or 3-4 days later, record hot. And then 3-4 days after that, record cold again. And you're saying, wow, the weather's crazy. No, you don't know the half of it. It's not weather at all. It's atmospheric physics is fucking with you. This is now permanent. This is becoming rapidly permanent because this will become a permanent feature. The heating of the polar vortex, because of global heating, the heating of the polar vortex becomes a permanent feature of the Earth dynamic system, or nearly so, or a frequent feature. And because of that, then all of these cut-off lows and highs and all of these oxbows forming in the jet stream, which used to work as a fence, now it no longer does. That also becomes a permanent feature of the Earth system. A permanent feature. Well, it comes and goes a little bit, but the coming and going doesn't matter. The fact that it's breaking down is what's permanent. Will it reform? Yeah, but it eventually will break down again. And the breakdowns of the jet stream and the warming of the polar vortex, these become trend lines. The polar vortex can never cool. It'll cool a little bit from day to day or week to week, but the trend line, because of global heating, the trend line for the polar vortex is to heat. And as it heats, it becomes more like this on a permanent basis, because that's what happens. I understand this is atmospheric physics. I understand this is Earth system dynamics. I understand that. I understand this is difficult. People don't even believe this. Too bad. This is reality. This is just as real as gravity. And it doesn't matter if you believe in gravity or not. If you jump out of the back of an airplane without a parachute, you're going to die because gravity is real. Your opinion doesn't enter into it. And what's happening here with the polar vortex, your opinion or your lack of opinion or your lack of concern about it doesn't enter into it. This is reality. Global heating is causing this. And this is not good. This is bad. This is really bad. This is about as bad as it gets, people. When this happens, you got a world of hurt. And when that happens, this happens. And these cut-off lows that have been breaking off of the jet stream and heading south, bringing cold core cyclones to interact with the warm, moist air that's naturally occurring down in the South Pacific, right? This becomes a thing. This is the thing. And when max velocity is saying, well, we're going to have record colds, by record we mean record breaking cold, record breaking all the way to Miami, record breaking cold all the way to Miami. The iguanas were falling out of the trees, frozen. And then right after that, record breaking heat. And people are like, what's going on with the weather? It ain't weather anymore, people. And your meteorologist cannot help you understand. They don't understand. I don't know if this is even taught in meteorology. I don't know that they ever see these pictures I don't know what they're teaching them. Are they teaching them any of this stuff? I don't know. This is a good one. It's a little more obvious what's happening here. Stable polar vortex, meaning it's a monopole, and it's cold. Then you get cold air contained by the strong jet stream. You see, they even labeled it correctly. So in this left half of this picture, of this illustration, stable polar vortex leads to cold air being contained by a strong jet stream. That's what I've been talking about this entire time. I mean, I know I'm repeating myself, but I have to repeat myself because this is little known information. And you must know this. You have got to understand this. This is going to kill people. Because this next diagram, where the wavy polar vortex is breaking down because it's not cold as it should be, and then this makes the jet stream weak and vulnerable to breakdowns, and then you have these pieces of it breaking off, and cold Arctic air is coming down, and worse, and it really is worse. The worst part is not that the cold Arctic air comes down into the northern countries, like Canada, the U.S., Europe, Asia, all right, even as far south as India. That's an inconvenience, and that will cause disruptions to rainfall patterns and agriculture and use of energy reserves like electricity or heating oil. That'll cause problems. But the bigger problem is that when the cold air descends, and this picture is really good at showing this, when the cold air descends, then of necessity, this is physics, warm air must ascend to replace it. And again, bears repeating. No one lives in the north, but the people who do experience this hot air. You don't, I don't, but they do. And when it ascends into and when it heads north and it ends up in the Arctic, then it melts the ice. That's really bad. Because if it's land-based ice, it flows into the sea and raises sea level. And this can be a catastrophic outcome. The melting ice doesn't have to take centuries, thousands of years. Melting ice doesn't have to take decades. Melting ice can take a couple of years. You can have enough melt water coming off of Greenland because of these sorts of things that actually it shuts down the AMOC. People don't even want to talk about that. Shutting down the AMOC, well, that better not happen. Shutting down the AMOC ocean circulation, okay, that's so bad that we're not even going to talk about that. They don't want to talk about it. They say, it's going to happen, but it'll happen by the year 2100, so let's not talk about it. I wouldn't be so certain of that, Buckwheat. I think you could be in big trouble because the Earth dynamic system is on the move, and there's no stopping this now. This is catastrophic. There's no stopping this. And we're seeing manifestations of it right here in California with these cold core cyclones. That's what they are, coming down to California and dumping and causing there to be rainfall events that are pretty unhinged. So this is I was supposed to be reading over here. Sudden stratospheric warming. This is the most dramatic change where stratospheric temperatures can skyrocket by 50 to 70 degrees Fahrenheit or more in a few days, causing the vortex to weaken and collapse. Like I said, last I heard, and it was a few years ago, no one knows why this happens. Maybe there's better science now. They're not mentioning it here. It has to do with planetary waves. Earth system dynamics, right? Impact on the jet stream. And the jet stream is lower in the atmosphere and therefore more pertinent. Impact on the jet stream. Disrupted polar vortex leads to a wavy jet stream. This causes the normally west to east flow to deviate, allowing frigid Arctic air to move south into the mid-latitudes. And warm air to deflect into the Arctic. That's bad. That's really bad. Oh, you don't want that. You don't want any of that going on because that's where the ice is. Weather implications. A weakened polar vortex and a wavy jet stream can result in colder than average temperatures and an increased chance of severe winter storms in mid-latitude regions. Again, they missed a part of this. A wavy jet stream can result in colder than average temperatures, and then 3 days later, warmer than average temperatures. This diagram on the right of what I'm reading, polar vortex explained, you see those wavies, those highs and the lows and the cold and the hot? They both happen. They both happen. And in the lower 48, they are having record cold, as it says here, colder than average temperatures, followed immediately, days later, by record heat. You think that doesn't leave a mark? You think that's not disruptive? You stop and think. That's going to be a problem. Why these changes occur? So now this is science, right? And like I said, a few years ago, this was not well developed, but things are moving along. Planetary wave activity. I'm going to say these things. You can look this stuff up yourself. This is Google. I don't expect you to, but if you don't, that's fine. I don't expect you to. But you need to understand that this is what's happening to you. The meteorologist is not going to explain this. I'm barely explaining it. I'm introducing it. This is first semester Earth dynamics, okay? Earth system dynamics. This is Earth system dynamics 1A, okay? This is your freshman year in college, and we're learning Earth system dynamics, and this is your first course. This is 1A. That's the level we're at right here. Planetary wave activity. Tropos, it's still going to be complicated. It's going to give you a headache. You're going to need aspirin. You'll fail Earth System Dynamics 1A the first couple of times you take the course. But since it's required for the degree, you're going to have to take it a couple of times. Welcome to my world. Tropospheric waves, which are large-scale atmospheric waves, can propagate upward and disrupt the stratospheric polar vortex, a process that can be amplified by conditions like enhanced planetary wave activity. Oh, that was really interesting. I have a tab open for that. We'll get to that in a minute. Dynamic interactions. The interactions between the stratospheric vortex, the polar vortex, and the tropospheric jet stream lower down in the atmosphere are complex, and their coupling can vary from tight to seemingly independent. The extent to which stratospheric disruptions affect surface weather is an active area of research. See, this is not well understood. It's hard to study this stuff. You've got layers in the atmosphere, and they're at the North Pole. So just think about the logistics. They do a lot with models, and they do a lot with satellites. This kind of stuff here. This is satellite data, a lot of it. Some of it's modeling. Excuse me. But they're just starting to wrap their hands around this. So the problem is they're studying a system that's on the move. It's moving. It's going somewhere. Solar and other influences. Some research suggests other factors such as enhanced solar activity can play a role in the lead up to an SSW event, sudden stratospheric warming, by influencing planetary wave activity. So there are complicated linkages. There are things called teleconnections. I think the next tab I'm going to put up here briefly talks about teleconnections. There are teleconnections, which means distant connections. And lo and behold, some of those distant connections include solar weather. Now, solar weather is well understood. We know what the sun is doing all the time. I mean, all the time. It's cyclical. It behaves in a cycle. And the cycles are predictable to a certain degree, to a large degree. We know what the sun is doing all the time. So there's no mysteries about what the sun is doing. What they don't know necessarily is how solar weather connects as a teleconnection to atmospheric physics. That's a new thing. And people in the denial-sphere and all those Dunning-Kruger pinheads, they think that the sun is getting hotter. It's not. There are events on the sun's surface that affect solar weather, and some of those may be linked to atmospheric physics. But the overall output of the sun is about the same. It varies a little bit. I see a number, it's like it varies by 1% or something. Now it's big and it's influencing the whole Earth and all this kind of stuff. But the sun's behavior, solar influences, are cyclical. And they're predictable. And even though if we don't know the teleconnections, we know it's cyclical. So any influence from the sun will be cyclical. And we know all about that. We know all about the cycles. But charts of the Earth system response patterns are not cyclical. They're linear, and they go up. The oceans are warming rapidly and in a non-cyclical fashion. And they haven't warmed at all for hundreds of years that we've been measuring. We don't see any changes in ocean temperatures that aren't attributable to Milankovitch cycles, ice ages, things like that. Things happen, but they're not cyclical. You see the difference? So if the sun was influencing, or I would say influencing, it is influencing, but if it was driving these changes, if it was driving them, then a swing in the sun's behavior would result in a swing in the Earth system dynamics behavior. But the changes we're seeing in the Earth system dynamics behavior is linear, not cyclical. It's fine that there is a teleconnection between the Earth's atmospheric physics and the sun. That's fine. That's okay. But it's not okay that the sun's solar weather is driving that Earth physics. That's not okay. Because the sun's behavior is cyclical and predictable, whereas the changes we're seeing in the Earth dynamic system are directional and linear and never been seen before. Things do change, but they should change in a predictable way if they're driven by the sun. Something else is driving the changes in the Earth dynamic system, and it's global heating, which is linear and directional. It's increasing at a known rate. We can measure it. And it's directional. It's not cyclical. It's not decreasing and then increasing and then decreasing again. Global heating is increasing. That's it. There's no cycle. Maybe there will be a cycle in 100,000 years or a million years. Maybe it'll go in another direction. But that doesn't count right now. Right now, the behavior of the Earth system was that it was stable for a long time, and now it's going someplace. It's called an excursion. And that happened rapidly, and it is now proceeding rapidly in actually an exponential fashion, but it's directional. The arrow was flat, and then the arrow went up. Whereas the behavior of the sun, sometimes it goes up, sometimes it goes down, then it goes up again, and it goes down. It's predictable. Is this not clear? So there can be a teleconnection to the sun's behavior, but the sun's behavior is cyclical and predictable. What's happening with the Earth system is not cyclical. It's directional. And up until recently, it was not predicted. It came out of nowhere. And it's continuing to worsen even faster and worse than expected. So the predictability you have over solar weather does not apply. They are not in sync. That does not mean that the solar weather does not influence the Earth system. It does. But the solar weather is playing a minor role in that influence. And the major role is caused by us burning fossil fuels and enhancing the greenhouse effect, which leads to directional global warming. And the direction is to increase it. Period. That's it. We're increasing the global temperature. We did that. The sun contributes, but it's not driving it. And if you don't understand that, you have my sympathy. Actually, you really do have my sympathy. This is complicated. Some of this is math. Some of this is understanding charts. Some of this is understanding the difference between cyclical and directional. They're just words, but it's complicated. And you have my sympathy. I don't expect you to understand that, ever. I never expect you to understand this. Never. You'll never understand this. Nobody will ever understand this. Your evening meteorologist will never understand this. That guy, he's got degrees. He may have a master's degree in meteorology. He'll never understand this, what I'm telling you. He'll never get it. He doesn't have time to figure it out. Now, I'm a system scientist. I have a predilection. I have a personality disorder that allows me to take all this data, put it into a big vat in my head, stir it a couple of times, and come out with understanding, comprehension. That's how I operate. I operate that way. That's my brain. I have a weird brain. Throw in a bunch of random shit and I put it together. Solar and other influences. I'll finish this one. Some research suggests other factors such as enhanced solar activity can play a role in the lead up to an SSW event by influencing planetary wave activity. So it's like it's indirect. It influences planetary waves, and those in turn influence sudden stratospheric warming, which in turn influences the behavior of the polar vortex. It's indirect. It's not even direct. And the cyclical nature of the solar activity is not reflected. It's not there at all. So enhanced planetary wave activity. I'm going to jump to this. It was a link on this thing. I clicked it, enhanced planetary wave activity. I clicked it, and I got another tab. And there's some verbiage here that I think is important because some of this is the meat. This is the meat of what's happening in terms of physics. So I'm going to mention it because I have to mention it. That's it. This is your reality. And I know you don't understand it. I know you don't want to understand it. I know you don't want to take the time to understand it. This is your reality. Gravity is real. This is real. This is happening. Deal with it. Enhanced planetary wave activity describes an intensification of the large-scale atmospheric oscillations, also known as Rossby waves, that shape global weather and climate patterns. Emphasis on the latter. These waves are fundamental to distributing heat and moisture around the globe. Yeah, that's the thing. Heat. Moving heat. And why is that? This is global heating, people. We've got some heat to deal with, and we're moving heat around, and it's going to suck. Okay, it's going to leave a mark. Recent research indicates an increased frequency of intense, persistent planetary wave events, a trend linked to climate change. Read 'em and weep. Read 'em and weep, my friends. Causes and contributing factors. Okay, here's what's causing the changes in the Rossby waves and the distribution of heat and moisture around the globe. Let's just take a look, shall we? They've got 4 bullet points. These AI summaries always have 4 or 5 bullet points. It's actually really helpful. Planetary waves are natural phenomena, true, but human activities, particularly climate change, are altering their behavior. This is where I don't like the use of the word climate change. This is AI, it's doing its best. But I know more than the AI does, and that doesn't surprise me, shouldn't surprise anybody. It's not climate change. Human activities, particularly climate change, global heating. Human activities, particularly global heating, are altering behaviors of these planetary waves, global heating, not climate change. Climate change will be a result of these changes. This cause and effect, okay? Climate change is not the cause. Climate change is the result. The cause is global heating. Global heating is physics. It's the physics of the greenhouse effect, which is real, planetary physics, which is being enhanced by excess CO2 emissions, also real, measurable, instrumental, and the excess CO2 comes from the combustion of fossil fuels, also real. Those are a thing. We do burn them. We release the CO2 in the atmosphere. Can't help it. When it goes in the atmosphere, it enhances the greenhouse effect. That's just physics. And when it enhances the greenhouse effect, you get global heating. There you go. Those are all the dots, people. Those are all the dots. You don't like some of the dots? Fuck you. Those are the dots. That's the outcome. That's how this works. And it's not climate change. Climate change is what you get when all that shit happens. I mean, you'd love yourself some climate change. If that's all you were getting was climate change, but you're not. You're getting global heating. And global heating is fucking us up. Okay? The distinction could not be more important. This is the key to the whole thing. Global heating. Arctic amplification. The rapid warming of the Arctic reduces the temperature gradient between the North Pole and mid-latitudes. That's us. This can lead to a slower, wavier jet stream, causing high and low pressure systems to become stuck in place for extended periods, a phenomenon known as atmospheric blocking. Yeah, that really sucks. That's what's happening in LA right now. Quasi-resonant amplification. I love this one. This occurs when high amplitude waves are in right phase to become trapped and resonate within the jet stream, significantly amplifying their strength and duration. Let me take you back to this, quasi-resonant amplification. Let's go back to this. You see these waves between the highs and the lows? These can become stuck. They become resonant waves, standing waves, a whole nother level of physics. I'm so sorry. Standing waves, oh my God. Let's not go there. Quasi-resonant amplification. This occurs when high amplitude waves, wavy jet stream, are in the right phase to become trapped and resonate within the jet stream, standing waves, like a guitar string when you pluck it, significantly amplifying their strength and duration. Yeah, that's another way of saying you're screwed. When the weather comes for you, it stays. Sudden stratospheric warmings enhance planetary wave activity and convergence of energy in the stratosphere, major drivers of SSWs. Temporary breakdowns in the polar vortex. Other influences, quasi-biennial oscillations, I've never heard of this, are in the equatorial stratosphere. Equatorial, that's the equator. El Nino southern oscillation ENSO events and tropical convective activity also influence planetary wave propagation and intensity. So the planetary waves in question actually they originate at the equator. So anything that happens at the equator can influence planetary waves. And the planetary waves then propagate north and south. Their influence, whatever's happening to them, propagates north and south because they're waves. It's like a waterbed. They're bouncy. And so if you bounce them at the equator, then the bounce moves its way north and south. But those are influences. I mean, how do the waves begin? Where do they begin? Why did they begin? And then they have their impacts, whatever those are. Again, cause and effect. The challenge for the planet Earth is that massive amounts of heat accumulate at the equator. The equator is really large. It's the entire circumference of the Earth. It's also a fairly wide band. It dominates the Earth's surface. Really, the equator does. Now, I know the people in the north don't know anything about the equator, but that's just a happenstance of history, that you happen to be located in the north of the northern hemisphere, and you don't interact with the equator. But the equatorial region is huge, dominates the Earth system dynamics. It's where all the heat, just so to speak, is generated. But it can't stay there. It rises into the upper atmosphere and then it splits. Some of it goes north, some goes south. But the more heat is being created at the south because of global heating, the more heat has to be dissipated. And this begins to affect planetary waves. That heat is going north. Some of it's going south also, but we're not talking about the southern hemisphere. That heat has to go north. And it goes north as fast as it can and as far as it can before it has to be, dissipate. But as it is pushing north and pushing north and pushing north, it starts to interfere with other aspects of the Earth dynamic system. The southern jet stream, for example, the subtropical jet stream, it gets pushed north. The Rossby waves get pushed north. All the circulatory patterns where the air rises, for example, at the equator, and where it falls, these get pushed north. Everything is being pushed north. And the ultimate destination of all this planetary disruption is this. And this has happened in the past. So we know that this is the destination. The ice ages and all this kind of cold baloney and the mammoths, that was all kind of a aberration. The normal state of the Earth system is that it is mostly the same temperature from the equator to the poles, and there's no ice. I'll repeat that. The normal, the most common, the most statistically relevant condition of the Earth is not the one we're in now, where we are dominated by ice ages, glacial maxima. There was one ice age. It started about 3 million years ago. But everybody calls all the fluctuations in the ice content of the Earth ice ages. Okay, so I'll just use that terminology. It's not true, but we'll go with that. The prevalence of ice ages, cyclical, repeated ice ages, okay? A lot of ice, not so much ice, lots of ice, not so much ice. This cyclical pattern has dominated the Earth, and it has, but only for about 3 million years. Apart from that little blip in planetary history, most of the Earth was typified by a different pattern. It was mostly the same temperature from the equator to the poles. We've never experienced that as humans. In fact, most of mammalian evolution hasn't experienced that. The dinosaurs were extincted 60 million years ago. We had the PETM 55 million years ago. Things really didn't settle down until about 40 million years ago. And 40 million years, that's a long time. But, mammals then had to develop. We had to have primates, and then we had to have bipeds. And about 5 million years ago, we were on the glide path to develop humans. And humans have been around, modern humans, Homo sapiens, have been around for only 300,000 years. We're deep, deep embedded in the Ice Age. The Ice Age has been going on for 3 million years, 10 times longer than humans have been around. We've been having cyclical ice ages, 10 times longer than we've been around. And even that 3 million years, that's just a tiny, tiny part of the Earth's overall history. And most of that history, typically speaking, it was more or less the same temperature from the equator to the poles. In the dead of winter in the poles, there's some hypothesis, and I've seen this discussion. The sun goes down and it's gone for maybe 3 months out of the year, because that's what happens at the poles. You have long days and then long nights, and that's because it's the pole. And so in the long nights, it would get cold, and there might be some frost, and organism would slow down, but it wasn't like there was ice. There wasn't. It was too warm for ice. So you might have some frost, you might have really cold weather, close to freezing, but otherwise, the rest of the year, it was completely different. So the ability of heat to move from the equator to the poles was not impeded in any way. Basically, there probably was no jet stream. And that's what we're seeing now. What we're seeing now with this kind of stuff going on, is that the jet stream is falling apart. It's weakening, slowing down, and then once it slows down enough, it starts to fall apart. And these cutoff lows, these cold core cyclones that have been haunting California since, a couple of months ago, these are manifestations of the breakdown of the jet stream. The jet stream is falling apart. That is inevitable. We know that's going to happen because at some point there will be no impediment of any kind between the movement of warm air from the equator to the North Pole. No impediment. There will be nothing to stop that. And the North Pole and everything up there, including Greenland, will warm catastrophically, and all the ice will collapse catastrophically. Period. That's it. This is the future now. There's no way to avoid this. And the unavoidability of this is planetary physics. And it is on a par in terms of unavoidability with the laws of gravity. Cannot be stopped. Cannot be avoided. There's no escape. There's no escape from this. Now, if we were to stop burning fossil fuels immediately, then we could disrupt these changes in the planetary wave activity. If we were to stop burning fossil fuels and therefore stop emitting CO2, then we could curtail global warming and maybe curtail some of the changes that we are now seeing, but we can't stop them. We can slow them down. Maybe things stabilize again at some point, but the damage is at this point is done. This picture here of the jet stream collapsing and no longer holding back the Arctic air, this picture is current. This is current science. This is not some projection into the year 2100 or something. This is happening today. And the effects of it are delivering cold core cyclones and punishing rain events to Southern California today. Literally the last month. They got one after the other of these things. And this is all manifestations of the collapse of the jet stream, period. The collapse of the jet stream is now proceeding apace. And when that happens, there will be no impediment to cold air sliding off the North Pole into lower latitudes. You're not going to like that. You can't stop it. And warm air sliding north to replace it, melting ice. And you're not going to like that, but you can't stop it. Can't stop these things. Here we go. Here we go, people. We're going. We're going there. We are going there. And this is today's data. We're already there. And we've been seeing this off of Southern California. We're already there. And in the other parts of the continental U.S., they've been getting waves, alternating waves of record cold and record heat and record cold and record heat 4 or 5 days apart. This is all from the collapse of the jet stream. Again, this picture, in particular the one on the right, when the jet stream weakens, it becomes wobblier, allowing cold Arctic air to move southward. Record cold. What they don't say in this picture is that warm air moves north. I mean, they have a little tiny thing over here that says warm air moves north. That's critical. That's like, oh, well, I don't care because I don't live in the north. Yeah, but that's going to melt the ice. And you're going to get sea level rise. And that's going to be a global phenomenon. And you're kind of basically, well, how do I say this in a nice way? How do I say this in a nice way? Hot air moving north and disrupting the formation and retention of ice. How do I say this in a nice way? Oh, I think you're fucked. You're kind of fucked. Okay, if you live in coastal Florida, which is like the lower third of Florida, get out. Just get out. Oh, I can't do that. Okay, fine, don't. But you should. When all those people leave Florida and they try to go find somewhere else to live, which they're going to have to do because sea level rise is inevitable. With the collapse of the jet stream, sea level rise, catastrophic, rapid sea level rise will be inevitable. You can't stop it. There's just no stopping it. And when that happens, and the people in the south of Florida, south third of Florida, Miami, right? Fort Lauderdale, they're going to have to leave. Where are they going to go? Will they be welcomed? Will there be housing for them? Will there be jobs? Will there be money? No, nothing for them. Nothing. There's nothing for them when they leave Florida. And you think that's not going to be a disruption? You think they're going to bring their guns, right? You think that's not going to be a disruption? Homeless Floridians living in front of my house in their RV with 6 AR-15s. You think that's not going to be a problem? Oh, okay. Yeah, I think that might be a problem. Can't be stopped. None of this can be stopped. We're in it now. We're in it. This is today's data. The jet stream is falling apart. It's gone. And this is today's data. That's supposed to be the polar vortex. It's been split in half. That's going to become permanent. We can't stop that. There's no way to stop this. We can't stop any of this now. So that's your lecture on Earth system dynamics. What a marathon. But this is your life. And everything that you thought was eternal and sacred ain't. It's just a contingent fact of history that you got to grow up and get your job and get your degrees and get your everything when everything was stable. But in the last 20 years, it all got blown to rat shit. And that's too bad. That's too bad. Here we go. We're in for it. None of this can be changed. It's all permanent. It only gets worse. And as it gets worse, worse things are going to happen. What are they going to be? I don't know. A complete collapse of the jet stream? Oh, geez. Oh, wow. Okay, well, I guess we're going to find out. I can't even predict. I mean, I can, but it's going to be ugly. Yeah, I can predict that. It's going to be ugly. Because the existence of the jet stream is why anything works the way it does now. And when it's gone, and when the melt of the Greenland becomes catastrophic and the AMOC is shut down, well, then the pleasure and the fun just piles on top of each other, don't they? So, bad news. It's always bad news. You come here for the bad news. Oh, baby, you don't know the half of it. Nobody knows the half of it. I'm just nibbling around the edges, and this is terrifying. Oh God, we're in trouble. Oh shit, we're in such trouble. It's just happening. There's nothing can stop it. This goes places where we've never gone. We've only been around 300,000 years, and the planet is now going to go someplace that human evolution has never experienced. No human civilization has experienced any of this. And yet, here we go. Will we be able to cope? No. Will there be refugees? Of course. Will they have anywhere to go? No. Are we going to save the people and get homes and clothing and food and water? No. We won't. So why am I here? Why am I saying all this? There's nothing we can do about it. We won't do anything about it. What's the point? I don't know. It has to be said. Someone has to say it. They're not going to say it on CNN. They're not going to say it at the COP31, and they're not going to say it in the next IPCC report. Someone's got to say it. Here I am. I'm saying it. Now we're in trouble. It's official. There's no turning back. My book is out. Link in the description. It was 100 days about what happens when the fossil fuels are shut off. And we could do that. We could do that. It's in the book. The book is written around that. Will we? Yes, we will. At some point, we will do it. When this gets bad enough, either we will do this or it will be done to us. We won't be able to continue. Too much disruption. Can't pull it off. Can't continue. Things just fall apart. And in the fragile global economy and the fragile global interconnectedness, it just falls apart. That's it. It's done. So when it's done, right? And on top of that, you're dealing with global heating. And on top of that, you're dealing with the collapse of the jet stream. And on top of that, you're dealing with a massive permanent change in planetary waves and Earth's atmospheric physics. Atmospheric physics. This is the entire planet, people. Get ready for it. Be watching for it. Be there. You're probably going to become a refugee. When? I don't know. Next year? Year after that? You're going to become a refugee. Well, I know because I happen to be somehow I hit the sweet spot. And it's pretty clear to me that we are right on the edge of everything. Right here in multi-dimensional phase space of the Earth dynamic system and the changes coming, we appear to be right here where I am in the Bay Area. For some reason, I didn't pick this place for that reason, but here I am and I'm looking at the changes and we just happen to be on the edge. We're edging. We're edgelords. And yeah, we in a good way. So yeah, I think we're going to be okay-ish, except for the refugees. Everybody's going to come here who can move themselves. They're going to come here. That's going to be a problem. But it's not the same problem everybody else is having. It's not going to be the same problem they're having in Southern California right now. It's not going to be the same problem they're having in Florida. We'll have a different problem. We'll have a refugee problem. We'll have an economic collapse. We'll have a collapse in food supplies. We'll have problems. But we're not going to have the problems everybody else is going to have. I don't know how that happened. I don't know how I ended up here. But we're here. So keep an eye out. And if you do keep an eye out, maybe you won't die. And that's my advice. Don't die.